The next speaker of this session is Raveendra.
Hello. Uh, Thank you. Good afternoon. I'm Dr. Raveendra, Faculty of Chemical Engineering at IIT Varanasi. Okay, thank you. Once again, thanks for the organizations. Myself, I'm Raveendra, Assistant Professor in Chemical Engineering at IIT Varanasi. So I will be going through quick technicalities on the importance of the flow fields to distribute the electrolyte in redox flow batteries, and we have several other applications of flow fields, let's say in lithium-ion batteries also, to distribute the coolant in a thermal management of lithium-ion batteries. And we have so many other applications of flow fields, like a kind of even the electrolyte distribution in electrolyzers also. So beyond this, let's go ahead with the present the importance of flow fields for redox flow batteries. So redox flow battery, as people may know much about it. So when we compare them with, let's say when we compare them with the solid state batteries, where we have the voltage and capacity are prefixed, and we cannot decouple them, and we cannot alter, we can manipulate them. So what we can have in flow batteries, we can decouple the voltage and capacity, and we can design the amount of time we can charge or discharge irrespective of its power level. Let's say we have 1 kilowatt power of the battery. We can discharge it for 2 hours or 5 hours, even 10 hours. It depends on the amount of electrolyte we take in the outside of the battery, where we store the electrolyte in an external tank. But where in lead acid batteries, lithium-ion batteries, we store the electrolyte inside the battery. That's why we are not capable to have a decoupling of the energy from the power rating. And anyway, the type of electrolyte we use in flow battery, we call them that kind of flow battery. Let's say vanadium use the electrolyte, we will call it vanadium flow battery. If you use the zinc bromine, we have a zinc bromine flow battery. And the cell voltage of any flow battery is a function of what kind of electrolyte we use in the flow battery. Actually, it's one of the complex system. It's not like a straight away plug and play and say. It's a kind of pilot plant. It's a kind of small scale plant to operate. It's not like a battery. So we need to understand them in many perspectives. Where we say in solid state batteries, we have efficiency, but here we have a lot of things. What kind of energy efficiency, coulombic efficiency, voltage efficiency. In addition to this, we have much more important one: how much of electrolyte we have utilized its capacity. Are we able to utilize its capacity to the 90% or 80% or 70%? And what type of health remaining in the electrolyte utilization or cycle by cycle. These are all parameters are function towards so many its inherent physical like material characteristics, like kind of membrane or electrode, or what kind of pressure drop or crossover is happening because of electrolyte circulation. So there is an interrelation between all these parameters. That's what my agenda to say. And it's not so easy to understand unless you go ahead with the complete experimentation and investigation into its physical understanding of the system. Then only you will come to know the reality of the meaning of what kind of strategies you need to tackle to improve its performance or efficiency characteristics. So in any flow battery, what we design is how to distribute the electrolyte over the anode or cathode electrodes. What people say, there are simple serpentine and interdistributed flow fields, which will increase whatever we want, which will decrease what we don't want. That's what the advantage of flow fields. But these are the very typical standard flow fields. It may be applicable in fuel cells or flow batteries. But how to design them for a typical flow battery, which we can deploy at an industrial scales. When we see literature on single cell or small size cell, when we compare them with the real deployable stack level demonstration, the optimized optimal reported flow electrolyte flow electrolyte values are very different. So we say 2 ml per minute per centimeter square is the best one when we go at a lab scale, but which is happening at a deployable stage, it's very different. It's like a 0.5 or 0.6. So there is no linearity between the results of what we have seen at cell level and what we see at the deployable stack. That's what there we need a real-time experimentation on different sizes of the cells, let's say 400 or 900 or 1500. And the real area will come to the how you design and how you fabricate it in your laboratory. These are the design cells designed at a laboratory scale. So when we see them, there are different optimal stoichiometric flow factors requirement, and the trajectories, how they affect the flow rate, how much capacity we acquire per a liter is different in different cells. So there is no linear. Let's say whatever we have at SF11, it's very good for SF11 here. But when we say 900, SF7 itself is very good. But when we say 1500, SF3 is itself very good. When we go beyond SF3 in 1500, it's giving us detrimental behavior. So we don't want SF11 and 1500. SF3 was very fine. So we need to understand how the electrolyte is distributing through these anodes, let's say electrodes, anodes, or cathodes, in order to capture the optimal flow rates for a deployable scale flow batteries. So for them, we need to understand the physical behavior of how electrode intrudes into the flow fields. There are kind of local geometry of the flow fields, which is a combination of its channel widths or depths or whatever it is. And we need to understand how it is compressible when we fabricate the battery. And we need to measure all those physical parameters through experiments. And we need to take these values to kind of CFD simulations or COMSOL simulations, and we need to solve these equations. And we need to design this flow fields at a deployable size, let's say 900 centimeters square or 1500 centimeters square. Once we solve them, we need to tackle how the electrolyte is distributing through the electrode. This is through the electrode, and this is through the flow fields. And we need to capture these contours with respect to wherever the local the area where we are citing. So we have to understand how the distribution is happening in either in electrodes or flow channels. And this is a characteristic of serpentine flow fields is it will maintain the uniformity respect of 400 to 900 and 1500. The benefit of it is there is a uniformity of distribution, but the problem is very huge pressure drop. So why it happened? When we understand this kind of flow distribution using CFD, you see here, when we compare 3 cell areas on a specific equalized area specific flow rate, the percentage of the fractional distribution of electrolyte to the electrodes is very different across the different cells. So on a 400 centimeters square, only 30% of the electrolyte is through the electrodes, remaining is flow fields. So this is through the electrodes, remaining is going through the flow fields without entering into or there may be internal mixing happening between the flow fields and electrode. So only 30% is flowing through or we can say convecting through the electrode, where in 1500, 66% is convecting through the electrode at the same flow rate. So that's where we see the split of momentum depends on the channel dimensions what we design for flow fields. So this is the major difference why we find a conflict in the literature when we compare the small size cells and deployable cell size. So that's what we need to tackle the quantum or momentum of electrolyte distribution in different flow fields using CFD or COMSOL. When we compare the serpentine and interdigitated, we see a lot of irrigation happening in the flow electrode. But when we see this, there is a maldistribution of electrolyte. There is a lot of unutilized white spaces in the interdigitated flow fields. So this kind of maldistribution is happening in IFF. And the serpentine flow fields, we have a very uniform distribution. As I told, serpentine has very huge pressure drop, which is not recommended because it's consuming the energy in the form of high pressure drops for the distribution of electrolyte. When we compare them electrochemically, definitely because of good uniformity of distribution, serpentine is giving us very good energy efficiency and better utilization of electrolyte, but very poor values for the IFF because it has a maldistribution. And there are many reasons we can justify why there is a kind of low performance for IFF based on their electrochemical kinetics, and the maximum current density will be limited to the IFF because of the low availability of reactant species at the electrode. As we have seen, the availability of reactants are very less in IFF. So, and how to capture, design them, or how to improve the statistics in the IFF? We can have so many taperings, so many local supports of pillars, so that we can deviate the flow in the direction whatever we want. We can have the guiders for the flow in the flow fields. It may be in the header or it may be in the local channels. We have to design such kind of flow guiders in order to improve the local distribution of the electrolyte in the flow fields. And what we have come across is okay. we have combined the serpentine and interdesiccated, where we have the continuous U-shape kind of serpentine and headed to local, the splitting of electrode from header to channels. So when we combine this, we got a flip-flop serpentine where without any physical barrier in the electrode, there is a directional changes happening for the electrolyte. In this way, we are able to have the low residence time for the reactant, and we can have a quick evacuation of the product species from the electrode, for giving the space for the fresh reactant in the electrode. So this way we got the understanding and designed this flip-flop. We patented it and we got the patent on it. And recently, I was with the Wipro Singapore actually for about a year. In that duration, we have filed 2 more patents by understanding the design of flow fields for the electrolyte distribution. And these 2 patents are under review in India and as well as Singapore. And when we summarize the design of flow fields, what we have in the literature is different what we design when we really go from small size cells to large size cells. That's what the engineering of an activity requires real-time study with the help of computational resources will give you successful results. Thank you. And you can contact me through this mobile or email. I will be giving you a positive response.
Thank you, Dr. Raveendra. Join me in thanking Raveendra for giving this presentation.